Hi, everyone. My name is Stefan Grosser, and I'm going to be presenting Black Box PPP is not Turing closed. This is joint work with Noah Fleming, Antonian Potassi, and Robert Robert. So let's jump right in with a classic problem. This is the problem of Pigeon, where I give you as input a circuit, taking in n bits as input and outputting n bits as input. And as output, I want to find either two inputs, X and Y, where the outputs of the circuit are the same, or I find some input Z on n bits, where the output of the circuit on Z is the all zeros function. Now, a nice fact about this problem is that it is total, and this follows just by the pigeonhole principle. Okay, so let's generalize these total functions into TFNP. So a search problem, R, which is a family of relations on n-bit inputs and solutions, which we'll call O of n. O of n always being of size at most polynomial in the length of the input. We want to find, as part of the search problem, on input X, some little o in O of n, where the relation R of n on X and O holds. Now, R is a total search problem if for every n-bit input X, there is a solution O where R of n on X and O holds. And even more, R is in TFNP if R is total, and given X and O, we can verify that O is a solution in polynomial time in the input size. So just as a sanity check, let's make sure that Pigeon is a TFNP problem. So, okay, I give you some circuit, and suppose I tell you that the solution is that there's a collision on Pigeon 0 and Pigeon 3. Well, then all I have to do is run the circuit on 0, 0, and run the circuit on 1, 1, and see that the outputs match. And that is a polynomial time verification. Okay, so let's take a look at the TFNP landscape. We have a bunch of syntactic TFNP subclasses, all corresponding to many combinatorial principles. So for example, we have PPP corresponding to problems reducing to the pigeonhole principle. We have a class PPA corresponding to the handshaking lemma, and PPAD for every DAG has a source or a sink. And there's a whole complexity zoo of TFNP just on its own. Okay, so let's more dive into PPP. So search problem R is in PPP if there's a many one reduction from R to this problem Pigeon, which we just defined. So here are some interesting facts about this class. So factoring is in PPP under randomized reductions unconditionally. And if you assume the generalized Riemann hypothesis, then factoring is deterministically reducible to Pigeon. As well, the Blichfeld problem, this is a computational problem corresponding to Blichfeld's theorem on lattices. This problem is PPP complete. This was shown in 2018. And further, you can show even more closeness between the pigeonhole principle and cryptography, where if FP equals PPP, then one-way permutations don't exist. Okay, so let's define the Turing closure. So given a class C in TFNP, we'll say C is Turing closed if FP with oracle access to C is in fact equal to C. And so you can think of this as polynomial time algorithms with oracle access to search problem C. This is in fact equivalent to a single oracle call to C, but possibly on a larger input size. So let's take a look amongst those TFNP classes I laid out before, which one of these are known to be Turing closed? And the answer is, in fact, all of them except for PPP, where we don't know, and it is conjectured that PPP is not Turing closed. So why do we care about this conjecture? So first of all, important problems like the approximate shortest vector problem, this problem is known to be in the Turing closure of PPP, but it is not known to be in PPP. And this is true of several other important problems as well in lattices and cryptography. So as well, it is a pretty easy observation that showing that PPP is not Turing closed, this implies that P doesn't equal NP. So of course, this means it is hopeless to actually show that PPP is not Turing closed, but makes it all the more interesting. And finally, relative to an oracle, FP to the PPP not equaling PPP, so PPP not being Turing closed, implies both logical unprovability and proof complexity lower bounds. So later on in this talk, we're going to hone in on that proof complexity aspect. Okay, so what does our work show? We show that PPP is not Turing closed, but in the black box model. Okay, so let's hop right into what the black box model of TFNP is. So let's define the black box pigeon problem, where as input, instead of a circuit, I just give you the function f from n+1 objects to n holes, and I output two pigeons I not equal to j, where f of I equals f of j. Okay, so let's define black box TFNP. A total search problem R is in black box TFNP if for every y, there is a polylog depth decision tree T of y, where T of y on x evaluates to 1 implies that x and y is valid in this relation, meaning y is a solution for x. Okay, so let's verify that black box pigeon is in TFNP to the DT. So here is an example of verification decision tree for if pigeons 5 and 7 collide. So let's walk down a few paths of this decision tree. First, we'll query pigeon 5 and see where it goes. Let's suppose that it goes to hole 1. Then we'll query pigeon 7. And if 7 also goes to hole 1, then we'll output 1. And if it goes to anything else, and this is what I mean by star, we'll output 0. And this procedure continues for any other option that 5 may go to. Okay, so it is easy to see that pigeon itself is in TFNP to the DT. Okay, so let's define a black box PPP. So search problem R is in PPP. I'm just going to stop saying DT from now on. If R has a depth polylog n reduction to pigeon. Notice there's an asterisk there. I'll get back to that in a moment. So what is a even a depth D reduction in this sense? Okay, so let's have two search problems. R on n unbit inputs and solution set O of R. This will have a depth D reduction to S, which on n-bit inputs and solution set O of S. If there are functions f of I mapping n bits to 0 or 1 for every I from 1 to m, remember m being the input size of S, and for every solution O in the solution set of S, we'll have a function g of O, which maps, it will map solutions of S to solutions of O. So just in the normal way reductions work, we'll have maps mapping the input for R to an input of S, and we'll have a reverse map taking the solution for S back to a solution for R. And all of these functions, f of I and g of O, are going to be computed by depth D decision trees. Okay, so now why the asterisk above? This is because we also don't want the input size to blow up too much when you transition from R to S. So more explicitly, when we go from n to m should not be too much larger. And in particular, we'll care about m being at most quasi-polynomially bigger than n. Okay, so let's put a picture to that definition on the previous slide. So let's say for just some random total search problem R of n reducing to pigeon of m, what does this look like? This means there's some pigeon protocol for R of n. So this means there'll be pigeons p1 up through pm plus 1, mapping to holes 1 through m. And for every pigeon, there's going to be an associated polylog n depth decision tree querying variables in Rn, and the leaf of every such path is going to be labeled by some hole from 1 to m, saying where pigeon I should fly, given those variables evaluating to 1 on this path, querying variables from Rn. Okay, so in this picture, we have P1 and P2 colliding on hole 3. So if this is in fact a solution in pigeon M, then we should expect that the reverse map taking solutions from pigeon to R will provide a valid solution for R. Okay, so what is it we prove? We show that a problem that is in the Turing closure of PPP in the black box setting is not reducible to pigeon. And this problem is extremely simple. It is just, as we call it, pigeon squared, where we put 2 parallel instances of pigeon next to each other. And all I ask you to do is find some solution for the left pigeon instance and some solution for the right pigeon instance. And notice even further, this problem is in the Turing closure non-adaptively. These pigeon instances are completely parallel and no adaptivity is necessary. So the goal for the rest of this talk is I'm going to introduce proof complexity techniques to extract a nice combinatorial problem equivalent to the above theorem. And I encourage you to look at our paper to see how we solve this combinatorial problem. So in the black box setting, all of these TFNP classes that I laid out, separations are known. So if there are lines between the complexity classes on the left, these are strict containments. And if there are no lines, then that means there is no containment in either direction. And we know these containments and separations to be true via proof complexity. Okay, so I don't have time to get into the connection in full, but the way you can think of it is for every black box TFNP class, this is captured by some propositional proof system where a problem is in this TFNP class if and only if this captured propositional proof system is able to prove in polynomially many steps or quasi-polynomially many steps that some corresponding CNF to this search problem is unsatisfiable. And a very nice aspect about these techniques is that not only do we get some random proof system associating to these nice TFNP classes, we get proof systems we deeply care about and have nice lower bound techniques for. So for example, with PPA, this corresponds to F2 null Stellensatz. For resolution, this corresponds to the TFNP class PLS. And unary Shirali-Adams corresponds to PPADS. Okay, so how can we hope to, using proof complexity, attack PPP lower bounds? Well, notice that PPP is right between unary Shirali-Adams and sum of squares, 2 semi-algebraic proof systems. And what this means is that unary Shirali-Adams is not able to prove a refutation of the pigeonhole principle, and SOS sum of squares is able to prove the pigeonhole principle. And lower bounds for both of these proof systems are given through pseudo expectations. So given that PPP is sandwiched right between these 2 proof systems, perhaps we can adapt the pseudo expectation technique in order to get pigeonhole principle lower bounds. Okay, so first off, what are pseudo expectations? So I'll call P and D to just be the ring of multilinear polynomials with real coefficients. And the pseudo expectation is going to be this expectation operator, mapping this ring to the real numbers. And this is going to be a degree D pseudo expectation if it satisfies 3 properties, namely that it is normalized. So 1 goes to 1. This operator is linear. And on any conjunction, the operator on a conjunction is non-negative. And in particular, we have a pseudo expectation operator for a specific total search problem R in black box TFNP. If we add this additional fourth point, that for any witnessing conjunction, this pseudo expectation will take its value to be 0. So what do I mean by a witnessing conjunction? I'll just give an example with pigeon squared. A witnessing conjunction here would be the conjunction that asserts that pigeon 1 maps to hole 1, pigeon 2 maps to hole 1, pigeon Q1 maps to hole 2, and pigeon Q2 maps to hole 2. Namely, it has found a solution to pigeon squared, this conjunction. So for any conjunction like this, it should be evaluated to 0 under a pseudo expectation for pigeon squared. So here's a nice theorem. There is no degree D Shirley-Adams refutation of an unsatisfiable CNF F if and only if there is a degree D pseudo expectation for F. And this is also true for sum of squares with a more restricted version of the pseudo expectation. So what we would like to do is modify pseudo expectations, add another bullet point, so we get, in fact, PPP lower bounds rather than Shirley-Adams lower bounds. Okay, so let's dive right into it and try to figure out what new bullet point we need to add to pseudo expectations to get pigeon lower bounds. All right, so let's say that our pseudo expectation operator is of degree n to the epsilon just some constant less than 1 for pigeon squared. And let's also suppose, for sake of contradiction, that pigeon squared reduces to pigeon. Okay, so that means in particular, there's some pigeon protocol for pigeon squared where pigeons 1 through m plus 1 all have polylogarithmic depth decision trees querying variables from pigeon squared. And these decision trees tell where the pigeons of pigeon m should fly for holes from 1 to m. And so let me make a notational definition here on the right in blue, where the pseudo expectation operator on a decision tree is equivalent to the sum over every path P in a decision tree, or root to leaf path, which we can think of as a conjunction by multiplying all the variables on that path, evaluating to 1, and taking the pseudo expectation operator on that conjunction. Now observe that if we sum over all the TIs here, the decision trees for pigeons 1 through m plus 1, that we in fact get the value m plus 1. And this follows from a very simple fact that if you take any decision tree at all and take the pseudo expectation operator on it, then this will equal 1. And this is true. You can see it simply because semantically, a decision tree is just going to be 1 when you blast it out into the sum of its paths. Okay, so let's do a double counting argument. Let me introduce the family HJ, which is the collection of conjunctions, namely paths of the TIs. So it is in particular a family of paths, P a path of TI for some I, and TI evaluated on that conjunction sends this pigeon I to hole J. So consider in this pigeon protocol, all paths of these TIs which map these pigeons to the hole J. Okay, so we have by our fact in the previous slide that m plus 1 equals the sum over pigeons I equals 1 to m plus 1 of the pseudo expectation on decision tree TI. And then we can actually double count by counting over holes that this equals the sum over holes J from 1 to m of the pseudo expectation operator on HJ. And you can see this just because every path in some TI is going to be counted by exactly 1 HJ, as every path tells some pigeon to map to some hole. And we are enumerating over all holes here. Okay. So now let's notice something. Take for some j, two conjunctions P1 and not equal to P2. So these are paths in two decision trees. Then by the validity of the pigeon protocol, either P1 and P2 witness a solution to pigeon squared, right? Because this pigeon protocol, solutions to the pigeon protocol have to map back to solutions to pigeon squared. So either these paths P1 and P2 find a solution to pigeon squared, or P1 and P2 contradict. And what do I mean by that? I mean that P1 will query some variable x1 in the pigeon squared instance, and it'll say that it's 0, and P2 will query that same variable, and it'll give it the opposite answer. So these two things can't happen at the same time. And what this would look like is pigeon S here would map to hole J, and whenever pigeon S does, pigeon T will map somewhere else, not to hole J. Okay, let's abstract this exact property we have here for our pigeon protocol. So let F be a family of conjunctions where for any C1 not equal to C2 and F, either C1 and C2 witness a solution to pigeon squared, or C1 and C2 contradict. And we'll say that a pseudo expectation is good if the pseudo expectation on F is at most 1. And by on F, I mean summing over all conjunctions inside F and taking the pseudo expectation on these conjunctions. So this is quite a strong property we might desire of a pseudo expectation, but let's assume this anyways. Okay, so let's assume this pseudo expectation we've been playing with from the start is in fact also good. Then we can run through the calculation we made before, and then further by the goodness of this pseudo expectation, this will be at most M, because each of the whole J's have exactly the property of these families F. So the pseudo expectation on each HJ will be at most 1, and we'll sum over M holes and get M, and we'll get M plus 1 is at most M, a contradiction. So what this implies is that if you can find a good n to the epsilon pseudo expectation for pigeon squared, then that means you cannot reduce pigeon squared to pigeon. So now with the remaining few minutes, let me introduce the candidate pseudo expectation, which we prove is good, and I'll define it by example. So here's a conjunction which reads that pigeon 1 in the first pigeonhole instance maps to hole 1. Pigeon 2 in the first pigeonhole instance maps to pigeon 3. And in the second pigeonhole instance, pigeon 2 maps to hole 2. So how will we assign it a value? We will assign it a value by pretending that this is a random matching. So with 1/4 probability, pigeon 1 will map to hole 1 here. And then now that we fixed that, pigeon 2 with 1/3 probability will map to hole 3 here. And then with a 1/4 probability, pigeon 2 in the second pigeonhole instance will map to hole 2. And so if you multiply these values out, you'll get 1/48 as the value for this conjunction. So here's a family of conjunctions where every conjunction is a different color here. And this is an example of a good family, but the value is much less than 1. So this follows exactly with the theorem we want to prove, which is that this matching pseudo expectation is in fact good. It's easy to show that it is a pseudo expectation, but it is a lot of work to show that it is in fact good. So I encourage you to see our paper for details on the proof that this pseudo expectation is good, and for several open questions and extensions on this work. Thank you for listening.